Hi, I'm Caitlin. In this video, I will demonstrate and explain our upgraded lock system. This is our hardware, where we have the RGB connected to the 5 volts as it is a common anode, the multi-digit SSD, the potentiometer, and our 2 push buttons. First, I'll talk about the SSD. This is a single-digit 7-segment display which has 7 LED segments labeled from A to G to show numbers 0 to 9. It can only display one number at a time, so we used a multi-digit SSD instead. Here is our multi-digit SSD, which has 4 cables for the digits and 7 for the segments. Each digit shares the same segment pins but has its own digit pin. We used multiplexing, as shown in our code, to briefly turn on each digit on and off, making all digits appear continuously lit while keeping the system responsive. This allows the countdown to display on the last digit during states 2 to 6, with low turning a segment on and high off, as it is a common anode, while other functions continue running. A potentiometer is a 3-terminal adjustable resistor that acts as a variable voltage divider. By reading it with analog read pin pot, we get a raw value between 0 and 1023. This raw value is then scaled using mapping to a usable LED brightness range of 30 to 255, so the LEDs never fully turn off and can reach a maximum brightness. A second custom function controls the RGB LED brightness, as seen here. It uses value scaling to convert each color input red, green, blue into the same potentiometer base brightness range, making the LED respond smoothly and realistically to knob adjustments. A realization arose that the RGB was a common anode, not cathode, like on Tinkercad, so we needed a way to reverse the values. That is why we subtracted 255 from the mapping reading, as a common anode RGB LED works in reverse, where the low values turn on and high values turn it off. This flip makes the brightness behave normally. The diagram on Tinkercad here helped us test our code and implement the real-life hardware. Additionally, the flowchart aided in understanding the various components that needed to be integrated into the code to make the lock system function correctly. For the serial monitor, the user must enter a password via the serial monitor to enable status reporting. Until the correct password is entered, no updates are shown. Once accepted, the monitor displays the current state, lock status, last input, and potentiometer value every second. The code reads input up. Finally, we get to the system functioning all together. But first, we must enter the password on the serial monitor. So now I'll demonstrate it. So here we have the green LED is on and the lock is free, and I'm going to press the unlock button and the countdown will start. So here we see the countdown starting. And then we are on to the next state, yellow color, and then we'll see the yellow flashing. Now the lock is engaged, and I'm going to press the unlock button now. The timer disappears as well. And now we return back to state 1. I will now demonstrate how the system works asynchronously, so we can see if the countdown or early sequence is running. Pressing this unlock button immediately stops the sequence and returns it back to state 1. Additionally, the potentiometer can still be adjusted. So as we can see here, everything is responding in real time. As I turn it, the LED gets brighter. And you can also see it in the serial monitor. This demonstrates how the analog input can control the output. So here I'm just showing some calculations for the toggle times for the hertz in our switch statement. So for frequency, it's just 1 over period, and then we are converting them to milliseconds, and then to flash them on and off, it's half a cycle for each, so then we'll just divide it by 2 and multiplying by 1000 before for the milliseconds to convert it. And so we can see in this graph, it's flashing from on and off every 250 milliseconds. So an aha moment is that I didn't realize you could use analog pins for other inputs, so such as the lock buttons, which was limiting the available pins for my multi-digits, and I watched lectures and I saw an image that you could use inputs, and this solved my problem. So the difference between working individually and as a team is that the workload increased, and it was potentially meant to be shared across members. Collaborating and sharing difficulties was a nice thing to do, like sharing the complicated tasks, as well as the goal to solve problems as a team. However, there was a little bit challenging trying to coordinate everyone together. Improvements from A1 to A2 is that the code became much more complex. We had to integrate the RGB LED, potentiometer, and multi-digit SSD, as well as the serial monitor password. So replacing those 3 separate LEDs required switching digital write to analog write, as well as removing Boolean declarations and creating a new LED control function. So that was the main differences.